This also came out of the
I calculated this juicy. I look on your file and see if I calculate the HSC one. What? Do you know the difference between HSC and HSC? HSC you like here.
Okay, we do have two presentations today. Very short research presentation by Fatima. So it will be a result of maybe less than 1 week effort in one important subject to start. So it will be preliminary results, but we need to discuss them. And then there will be a second presentation, Literature Club by Levi. Oh, okay.
I don't see Brandon, right? He's not here.
Brandon's not here? We need him. Send
Does
him
he
in.
know about it? What
Should
does he
I-
know?
Can you send him?
I told him that Levi is present.
Can you send him an email
Yeah, I'm
telling
gonna-
that his expertise is needed? There are a couple of printouts to share.
Веришь в джеда.
Yeah. Please go ahead.
Okay.
Today I'm going to talk about the functionalized single world carbon nanotubes by Adult Group. Momentum result dynamic study by density functional theory. Here is the short outline. First I'll talk about the motivation of this research and then ground state electronic structure. The motivation is the functionalized carbon nanotubes have applications have many applications, including fabricating nanobioelectronic devices and chemical functionalization controls the electronic structure of carbon nanotubes also. And you know, the K-dispersion is important for any periodic solids. Here is the model of a group modified carbon nanotube.
So can you explain what is on this model, which atoms and how they are arranged?
So it is, I believe, bromobenzene. It is attached to the lattice of carbon nanotubes.
So why there? You have this benzene ring coming out of the nanotube, and nearby there is a hydrogen. Why it is there? What's the reason?
Because the structure was given to him.
But later on you'll be writing paper on your own. So what's your?
She is not a chemist, right?
She is a chemist.
She is physicist.
No, she's physics.
Oh.
Are you?
Yeah.
You have PhD in physics, not chemistry. So
But what is your
she's
guess?
excused not to know this.
Yeah, but we can make a brainstorming just to decide what.
I will know eventually, not like after sometimes, probably.
But what do you think? Why the hydrogen is needed?
Are you doing restricted or unrestricted DFT? Restricted or unrestricted DFT?
With spin polarization,
Only,
Yeah,
that's the next question.
unrestricted. Restricted.
How big is this carbon?
so if you remove this hydrogen, what will be the number of electrons? Well, no one expects you to count number of electrons right now, but will it be even or odd? If you remove hydrogen, but if you put it there, it will be even number of electrons, which will make the system more stable. Okay? Okay, please keep going.
So here is the ground state electronic structure for singlet state at gamma point and spin orbit coupling. So first,
Oh, which one is which one? Top is.
so one is DOS, another is
But those without spin orbit, right?
Or is everything, or everything is with spin orbit?
spin orbit coupling.
Everything with spin orbit, each
Oh.
of 3 panels.
So you don't compare those without and those with. You're just showing everything which has already spin orbit coupling.
Yeah, spin orbit coupling, and later on I'll show spin polarized.
But can you briefly summarize, there will be several figures with results, and can you just give general structure of results? Which results are you going to show?
So I'm going to show singlet state, triplet state, a singlet at gamma point at 3 different K points. And triplet also the same at gamma point, and gamma point is with a spin orbit coupling, and another one is a spin polarized. And K points is also same with spin orbit coupling and spin polarized.
Okay,
So I believe 4 sets.
okay, 4 sets.
And for gamma, only at gamma point with the spin orbit coupling, I'm going to show the absorption spectrum and EDOS. Rest of them are not.
What is the EDOS?
Excited state?
No, I guess is projected DOS, right?
No,
Seems like one.
just share your vision. It's results composed in like very short time, so it's fine to tell something
It's
wrong.
excited dose, right? The dose of excitons. Of transitions, of optical transitions.
Yes, right?
Yes.
It's different from your spectra because spectra is taking your excited dose multiplied by what? How your spectra on the top different from EDOS.
Here oscillation strength is
Right. So technically, if you now multiply each of the states by oscillator strengths, you will get the absorption spectrum.
yeah.
If you not include the kind of weight with respect to the oscillator strengths, you will just get this EDOS. I missed, what is the red one? How, like, you have the shape?
Speaker should answer, but I have a guess that there were technical problems. The red stuff should protrude up to black line and should signify occupied versus unoccupied.
So the difference is not meaningful.
No,
It's meaningless.
no, it's factor 2 is missed here.
Okay.
Feel free to stop and ask questions. Especially.
I do.
So why does your EDOS plateau from around 0.6 to 1.3? How does it plateau? Because you still have features going on. So how do you get a straight line where you don't in your DOS?
What was the broadening parameter? It looks like it was just by mistake artificially high broadening parameter that they all are not resolved.
That's why your range is so small.
Yeah.
You can have all possible transitions to much higher energy.
Yeah.
why you stop at 1.5.
So
Like, just looking on your doors, you should have the transitions at least up to 3 electron volts, right? From the very lowest energy presented in the doors, 1.5, minus 1.5, up to the very high electronic level from the doors, which is 1.5, right? So you should have these transitions, and I completely agree with Levi. You have features in your doors which should be represented in your excited doors as well.
And I do have a question about your spectrum. The last line at about 1250 nanometers, is it the lowest transition, or there is something lower than that? So if you go to red at about 1500, the line doesn't go to 0. It is still on 0. Will it go to 0 after? What's the low? Is it the lowest transition, or there is one more?
Yeah, there are a couple of more.
Okay. So next time try to show all the lowest transition are most interesting. The primary goal of this project.
So is your band gap like a quarter of an EV, or is it just due to the broadening that it really goes to 0?
It's not 0. I think 0.6 or something. 0.6 or no, yeah.
The gap is open, so it should not go to
Yeah, but
It's broadening.
it's very broad, and the tail is going close to 0.
Yeah, it looks like the broadening parameter is a little larger than optimal.
Timo, a question. What does the E stand for in the EDOS?
What?
What does the E stand for in the EDOS?
It's like excited.
Electronic, like e-commerce.
Oh, okay.
Okay, excited state. Excited.
I will answer this question.
Ah.
If you look on the all possible transitions, right? You start with the lowest possible transition, homolumen transition, right? And this is this. Then next. So E stays for transitions, right? But to make them this way, you need to multiply by the oscillator strength, right? And this plot not really doing it. It's just showing all possible transitions independent whether they're optically allowed or not. Means whether they have transition dipole moment not equal to 0 or they do. This plot doesn't really show you. It's just showing you all possible transitions from occupied to the unoccupied levels. That's it. Thank you.
Thank you.
So E stays excited. Those.
Can I go ahead? And this is yeah, singlet state at gamma point has been polarized.
We had a question about the
Same thing against the broadening. So the broadening parameter is like high for all of these density of states, not for all.
So wait. Can we stay here? Spin polarized, or what Jabat asked, or Levi asked, spin unrestricted. DFT means that there is a set of orbital energies for spin alpha and spin beta.
Spin up and spin down.
Yeah, spin up and spin down. And here you show only one density of states. Why? If you're telling that it is spin polar, why it is only one line, not two? In some figures which follow, you show those part of the dose coming up in red, part of the dose coming down with blue. And here it is only one. Why?
I think it's gamma point.
Huh?
At gamma point.
No.
Or spin is 0.
Spin is 0, which means
Ground state.
which means how energies of spin up, or like HOMO with spin up and energy of HOMO with spin down, are they different or equal?
Equal.
Yes, and therefore probably you decided not to show spin down component because they are the same.
I don't see any state for spin down.
Hmm?
The outcome for
No, there should be spin down if you are telling that it is spin polar, but you may not. You may skip it. But for comparison, for not misleading audience, it's better to show them down and show that they are absolutely symmetric. Yes, please.
And this is also for singlet state, spin polarized at 3 different K points. So later on I will calculate transition rate at 3 different for 3 different K points on this model. So here I would say band gap is increasing. So at K equals 0.3
Increasing for
band gap.
for what again?
So can you just show it on the figure? How do we see that it is increasing?
In case of what again? What's the reason for the increase of the gap?
Because
Very
the
different
K values are increasing. Band gap is also
So
increasing.
you just take different key points.
Yeah, later on I will add them all.
Okay. So and is it from your previous preliminary results? Is it direct or indirect gap? Do you like if it is direct gap in gamma point, then it is expected that with larger K point the gap will increase.
I didn't draw dispersion.
No, functional.
Then later I realized that.
Where's keys? No.
So what is the Kx, Ky and Kz in your calculation setup for this one, for the last one?
You check it.
What was the question?
What is your setup in calculation like Kx, Ky and Kz?
I don't know.
It is a no, you do know. It is a provocative question with evident answer. So can you go back to your system, the model? So what is x, y, and in along which direction your K points are changing?
Z direction.
Yes. Are there any K points along x and y? Is there any chance for of non-trivial effects of electron moving along x and y through the
I
vacuum?
think so.
So probably
Just Kz.
yes. It is like
For
1, 1, 3.
Then I'm just wondering why is, oh okay, that's why it's 0.4 to 6.
Yes.
Oh, no, yeah, not X. But for spin polarization, I think we are considering X axis and Z axis for spin polarization.
But the result that you are showing, there is a K points distribution only along
And Z
Z
axis.
axis.
Only Z axis.
Yeah. And the spin orbit coupling DOS is missing here. Now, for two-plane states, a spin polarized, we are considering x-axis here, and for 3 different K points. So these are the DOSes at 3 different K points.
So is this along the x-axis?
I'm going to increase it so that we can focus maybe on one of them if it is. Does anyone know how to increase?
I think you have to escape and then go back again.
Hmm?
No, this axis.
Now zoom in.
Can you just show?
Sure.
Yeah, zoom in on with the first one.
But figures and do different. Figures and do different. Cause the Z reaction.
Hmm? 6.5?
Instead of zooming in, just make the image larger.
I think you got there. It should be sufficient. So, can you comment on difference of red and blue field areas?
Which one?
Yeah.
Okay. So show are they blue and red equal? Are they symmetric in respect to the zero axis, or there is a difference? And if
There's a
there,
difference.
so why and how to interpret it?
So the blue one is for spin down,
Uh-huh.
and red one is for spin up.
Okay.
So there is a band gap for spin up.
Uh-huh.
And for spin down,
It looks like there is no gap, or gap is
looks
minimal.
like there is no gap.
Okay. And if one decides to integrate the area, red area and blue area, will they be equal or different?
Different.
By how much? And why they will be
Why
different?
band gap?
No. The area. The area in the curve is number of electrons. What is the number of electrons we spin up and we spin down?
This two electron difference.
Huh?
Two different.
Yes. Spin up will have two electrons more than spin down. So so in your results, this looks like, at least for interpretation, as former HOMO, and this as a former LUMO for singlet, and this would be as former HOMO and former LUMO. So they offset along energy, and then the electron from spin down is HOMO is taken and promoted to LUMO of spin up. So the total number of electrons here will be 2 more than here. So there are several effects. Change of energies. Like this is HOMO down, this is HOMO up. They are shifted in energies. And another change in occupation. So HOMO down get depleted, nothing, and LUMO up get additional electron. Okay.
I mean, in principle, all this should be spin non-polarized, right? I mean, that's what that little hydra use for.
Let me answer this question. Triplet state was requested
Oh,
by,
this is triplet.
mandated by constraint DFT. By
I see.
requesting the number of electrons up and down will be exactly 2. So it's under restriction that.
Wait, okay, I
Okay.
see, I see.
Okay.
I missed the triplet part.
But this makes not really physical meaning for the triplet in the ground state.
Later on.
Because we need excited state triplet.
Not everything at once.
So did you get any
No, we
difference in
want
the different
everything
cap
at once.
ones? What is the reason of controlling the different cap ones? Band gap change or anything like that?
So, because we are going to study direct and indirect transitions that are around like the silicon nanowires, right?
So you
Here we know that the bright state in these tubes is, I mean, the low state in these tubes is bright because they emit. And if they emit, it cannot be not direct transition.
wait. Wait.
This is
Uh,
result.
I'm answering first to Jabet and second to Professor Kilina. So probably, Fatima, you are thinking, you are anticipating that since it is a periodic structure in z direction, there will be additional effects to optical properties due to momentum distribution. And you just try to systematically include it into calculation. Right? So the second part of the question, most likely the transitions without change of k vector in the gamma point will contribute at most for emission. It is expected. But just for having a systematic consideration, additional transitions are planned to be included.
No questions?
So there are density of states at the gamma point. And then you include k points and you look for what dispersion fields. How flat or not flat are they?
Don't ask me, ask the presenter.
I'm asking.
Yeah,
Okay.
I need to draw dispersion curve
So now
and see how
let
they're
me
going.
contribute. In some sense, this set of three replicas of density of states at different k points is a not very optimal replacement of dispersion curves.
Well, let's go back to seeing that.
Okay.
Do we have discussion
Can we go back to slide 7?
No, I don't.
That's
I
not
don't have
No,
dispersion.
something to think about.
Let's go to slide 7 by request of the audience. It's 9?
Oh, slide 7.
Yes.
So just a second, are you answering the question or what? Why we go to
Yes,
the
yes, yes. She's answering the question of Professor Krzyzewski.
What is, yeah, please. What is spin polarized? Remind me, please, in this case here. Is it the spin constraint? Or
Yes, it's spin constrained for have zero spin. Spin up and spin down are equivalent, and therefore spin down is not shown here.
right. So spin non-polarized then. I mean, that's what they typically do to, to see the effect of
So,
K points.
answering your question, the dispersion curve is not flat. If one zoom in this figure and looks on the gap,
Oh, I see that. If,
so it's evidence that it is not not flat, and maybe taken into account, dispersion is not a stupid idea.
is it worth pain and suffering of K points?
Probably.
So, returning back to your kind of closed gap, I don't know, technically the electronic structure in this case makes probably not much physical sense. What you can, like, if you really want to use your not correlated results without excitonic effects, then you can just take total energy with spin orbit
Mm-hmm.
and then subtract from the total energy of the singlet according
Right.
to your calculations, and then this energy would correspond to the position of, well, roughly should correspond to the
Correct.
position of your triplet
Yes.
state.
Yes.
But then
so if you
if you go to-
look on the blue table at the end of presentation, you will see.
Oh, you do it.
Yes.
But returning back to your red and blue slide with spin down, spin up distributions, I still kind of like what exactly this information is given to us, because this is what? This is the electronic structure for the ground state.
Yes.
If the ground state of this system was triplet, then the system is metallic. This is what they're telling me. What? Makes no sense.
Why there is a conclusion that it is metallic?
Because you have no gap.
Well, there is no gap if we add together up and down, but each
No, you're just looking from up to up and from down to down. Your gap is closed.
Because your up electron has one in the form of LUMO, so it's closed, and then the bottom one has one taken away from LUMO, HOMO. So then you have HOMO minus one that is occupied. HOMO is not occupied.
I see. So you're taking that it is very suspicious,
Yes.
and suggest that one should check it with more optimization. If optimization was done for triplet, or the same geometry as
I think
single.
optimization is done.
So things to check are optimization and second the hybrid, because this reduced gap can be a shortcoming of the pure DFT. Okay.
Pure D.
Potentially suspicious effect of too small gap.
So here is the triplet for triplet state at gamma point. It's just like here the density of states, spin orbit coupling, and corresponding absorption spectra and etas. And that one is triplet state at gamma point, spin polarized.
Are you going to go to next slide? Let's discuss this one for a little longer. Let's discuss for the previous one. Okay,
Which one?
previous one, yes. So what do you learn from there?
Yeah.
Like,
From which one? From the absorption spectra?
well, from comparison, from density of states with spin orbit versus spin polarized. Like, does it show the closed gap that induced suspicion with spin orbit in presence of spin orbit coupling?
So looks like a spin orbit coupling, a DOS for spin orbit coupling showed up. So there is no band gap.
It looks like there is a gap. The gap opens.
in spin
It,
orbit coupling.
on one hand, it contradicts, it differs from spin polarized data. On another hand, it shows that there is a gap and it is not metallic, which is maybe good.
So you mean that for spin polarized it shows that it's metallic, and for spin orbit coupling it's not metallic. Okay.
So spin orbit coupling opens the gap.
Well, at least the figures look this way.
What was it like? 1/137 squared.
What about
Also known as 10 to negative 4.
It is not only this effect, it mixes orbitals and then they split differently.
Okay.
So what about the spectrum with spin orbit coupling? Is the
Yeah.
peak at 1200
It continues.
is the lowest one?
No, it continues. I think around 3,000 nanometer.
Okay, we need to focus on this range because infrared emission is main goal of this research. Okay.
What exactly is this absorption spectrum? So this is.
Can you explain what is the? Just explain what is on the figure.
So it starts absorbed from 500 nanometer, and it continues up to 27.
No, just explain what are the axes, because in physics community and in computation and theory, many people prefer electron volts, and here there are some.
Well, that's fine. Nanometers are fine.
Okay. What else?
Is it triplet, right? What's the photon that is being absorbed produces triplet. I mean, is this the meaning of this absorption?
Absorption from triplet ground state to triplet excited state.
Oh, man. Okay, I see.
Can we identify the nature of these peaks? Like in carbon nanotubes community, there are typical E11, E22 transitions. Is it possible, maybe not now, but in future, to identify those standard transitions?
Okay.
Okay.
So this is like if you constrain the ground state to the triplet, and this is the absorption. So triplet to triplet excited.
Okay.
And then
Yeah.
You know what? Your triplet to triplet absorption looks very much the same as singlet to singlet absorption. Identical, I would say.
Identical?
Yeah.
Can it be a human error of showing the same figure, or it is
so the spin
really
polarized,
very similar?
spin polarized one.
It is, I think, slightly shifted. And the oscillator strength at like
So,
1500 is smaller. I mean, the yeah,
I don't understand.
different.
So what the question was that absorption spectrum on slide 9
And 8.
seems similar. No, on absorption spectrum in slide 5. Not 6.5. Yes. So the question is how similar or how different they are. The absorption spectrum. Maybe you can copy paste and show them together. If you are in the
Would it be possible to also copy the DOS?
Maybe, and then it will give you less chance to present yours.
No, because
Yes, but
looking at it, the DOS looks identical, or nearly identical.
okay. So number of peaks seems the same, 4 large peaks. Position of peaks very similar, but
There's a difference. You look at the end of the tail. Like there's.
Well, that's
bottoms
maybe
up
just
point.
line width.
no. The one for singlet seems to go up after, and one with triplet seems to go down. Maybe the best way would be to plot them 2 lines on the same figure to see to highlight the similarities and differences. Okay.
The difference, I can see the difference in absorption coefficient on y-axis.
Okay.
So that's the UV spectrum view. So that probably won't be affected by the functional group as much,
Mm-hmm.
or the changes near the gap. So,
Yeah.
so it's probably nanotube absorption. I would assume anyway.
Why what?
Aaron suggests that if one would show spectrum also continue to the UV range in the like 3 to 100 nanometers. At this range, absorption of a singlet and triplet configuration should be identical, because the singlet and triplet configuration affects only frontier orbitals. And it will be a good reference point. They likely will be coinciding at UV range and start diverging close to IR range. Am I interpreting you right? Okay.
But you're claiming it's not from singlet to triplet, it's triplet, triplet.
I interpret it this way.
But then why is each singlet in your regular spectra will have sub-triplet structure, right? It's not just low state which will have a triplet state, it's each of them. Each excited state will also have a sub-triplet range of contributions. So they might be different as well.
We can check it.
Like your triplet state, like in a nanotube, you have E11 band, E22 band, E33 band, and so on.
Yes.
And each of these E11S band will have T11 triplet band,
Yes.
T22 triplet band, T33 triplet band, up to the UV or whatever range.
So the offsets from E11 and E22, how far they different from T1 and T2?
E11 from E22, usually in the range of 1 electron volt difference.
And from T1 and T2?
I have no idea, never seen the triplet emission. Or triplet absorption.
Okay, so what is on this table?
You can assume that your triplet might have, although not necessarily, but roughly maybe you expect that offset of your triplet with respect to singlet in each band would be similar. Like if your lowest band is offset by half of electron volt, triplet versus singlet, then the other ones will be also shifted by the same way. But I guess this is exactly the question which you might address with your calculations, although not in a way how you do it.
So what is on this table and how to interpret it?
Here we can see the band gap and total energy.
Okay. So should we look at the configuration that gives minimal total energy as most probable?
Yeah. Good idea.
Doesn't it depend on methodology?
So which one gives the lowest total energy?
So x-axis left.
No, just tell and give the
So
numbers.
x-axis triplet at ground point, spin polarized up. No. Spin polarized up.
No, it looks like
No, you're singlet.
singlet K point spin polar. The third line,
Oh, okay. Then.
minus 33,
This
82.
is negative.
Yes, negative. One should look for lowest one.
Yeah, singlet K point spin polarized at K point 0 point.
Which one? Can you again
The
point?
third.
Can
Or
you
give
just
me
show
the
it?
number? What is
just,
the number you're talking about? So it's 3,381 period 9964. This is a value which is the lowest. Oh no,
Negative
82. You have 82. Sorry.
382.
Yeah,
The
this
third line, yes.
singlet. Yeah.
So if you take into account K
Does it
points,
mean that your singlet is lowest in energy? I
this
mean,
is ground state singlet. S0. It's not transition.
well, singlet gamma SOC or singlet gamma. No, what else you have? Singlet gamma SOC. And the next one is singlet K point spin polar. Like you have two singlets here, which has the lowest energy. Which, and it looks like you have a little bit more negative value for the singlet K point spin polar K equals 008, but again, does it mean that your lowest ground state should be polar? I cannot understand what exactly is the physics behind it. Why your singlet state is polar? What is polar?
Wait. Your question is about physics or about notation in the table?
Both, because
First,
notation should
no,
correspond
wait.
to the physics.
First, we should agree on notation and then discuss physics. So what does polar means in your notations?
Spin polarized.
Calculation. So it's a type of calculation.
Yeah.
So you can have singlet computed with spin polarized calculations. It's just you take I spin equals 2 in your in-car. Okay. So this polar one.
But your ground state for the singlet should be, the low state should not be polarized as a ground state.
But who forbids you to any of us to compute ground
You
state?
can compute
in
whatever
singlet?
you want, but your lowest energy corresponds to the polarized case in a singlet, which is against the intuitive physical kind of situation.
How much it is lower?
I don't care, I don't know what your units are.
Electron volts.
Spin non-polarized. Do you have it for reference? Is it lower? Just to know the expected ground state.
It looks like according to the results, singlet polarized case should be the lowest ground state. But this is not the case.
So calculation of
Intuition.
singlet. Your confusion and protest is related to the difference of ground state singlet with and without spin polarization. Intuitively, one would expect them to be the same.
Actually, if the ground state should be without any polarization, it should be the
Spin
lowest
singlet.
energy.
Well, there is a technical opportunity to compute ground state in presence of spin polarization in the code. It doesn't mean that anything is polarized, but one can keep tracking of spin up and spin down.
But
So what's the magnetic moment of this ground state?
then what is your...
Zero.
0.
So it's
Whew, okay, cool.
so you do not have objections then to
I was
this.
just sitting behind Sveta. What is the k equal 0, 0.8? I mean, the ground state should not have any k point labels on it.
I'll say, do it in this K point.
No, I'm sorry. You introduce some k points and then DFT does its thing and spits out at you a single number.
Wait, let me please correct me or answer yourself, Fatima. I'll try to tell how I interpret it, but you may want to correct me. Total energy is computed in presence of distribution of k points.
Yes,
So it's a single number, including all k points.
k points. Yes.
All k.
Yes. Okay.
But then, in the same table, there is another column with band gap.
Right.
And band gap is different at different k points.
So it's the band gap at this.
Right.
Okay, I see.
At least it's my understanding. Is that what you did? So the total energy for all k points and band gap is for the one that gives the
Exactly,
minimum.
yep.
Okay.
Total energy for all k points, spin up, spin down.
Okay.
But band gap different.
And what is energy difference between singlet and triplet? Ground state singlet and the lowest triplet. Like if you subtract.
So ground state singlet means spin or polarized or spin away.
Well, in each of them, what is the results for energy difference between singlet and triplet? In spin polarization on one hand and with spin orbit on another hand.
It's very low.
But approximately, is it?
Like 0.6 for k point
0.6.
0.08. The bottom number and the bottom singlet.
Okay.
Right, because it's negative 3,382.024, and then you minus negative 3,381.41. So you can approximate the first one as 2, and then 1.4, so 0.6.
So 0.6 with K points.
K equals 0.08.
Okay. So the difference between singlet and triplet is, can you repeat just your arithmetic? Not the process, but results, the numbers.
Take
Just give two numbers.
Not
Negative
process of the number.
3,308.
No, the result.
Oh,
Result.
0.6 EV.
0.6 EV.
Yes.
Brandon, from your experience, what is singlet ground state to triplet energy difference?
It's kind of there. There's quite a few triplets below the first excited singlet state. So
And from ground singlet to first excited singlet?
about 1.
About 1
Definitely.
for 6.5. So the number 0.6 is in the reasonable range.
But if you do the spin orbit coupling at gamma, you get
Then it
virtually 0.
okay. So spin orbit gives some strange results, and without spin orbit it's reasonable.
And at gamma, for the spin polar, you get about the same, a little bit less.
Okay.
Okay, this is the last slide. Then acknowledgement. I would like to acknowledge Aaron.
Well, you're telling if something is wrong, blame her.
Not to mention Dr. Keelan and so.
Okay, let's
Thank
thank
you.
Fatima for presenting and being ready to dive into a completely new area and other more questions.
I have a quick question. So on your table,
Stay.
you say your band gap for your triplets are, without spin orbit coupling, the other ones are about 1/4 of an EV. But if we look at slide 8, I believe, where you do triplet K-point spin polarized, it doesn't appear that you have 1/4 of an EV between your occupied and unoccupied orbitals. How did you get that value?
Which one? You need to repeat the question.
So you set your band gap for x-axis triplet gamma spin polarized is 0.27.
Spin polarized up or down?
They're the same
Oh,
numbers.
also the same.
But looking at your DOS graph, you don't see a really big change of density. Can you explain that, or?
This one.
I think that would be a corresponding one.
Oh, this one not.
No, this is for triplet, so the next slide.
This one.
Any of them for triplet. You say you have it.
Just let's focus on one of this.
Yeah, this one.
Yeah, and enlarge. Yeah, enough. Otherwise, it will be.
So now the question.
So you say you have a band gap of about 1/4.
So it doesn't
of
look
EV,
like the band gap is
but it
this
doesn't
much?
look like that is there.
What is the x-axis range? It's really shows very wide from -10 to +10 electron volts, and we are speaking about like 1/4 of EV.
So like,
So it's maybe visual because of the Again, not optimal width parameter. So if one would redraw it for a narrower range, maybe from -2 to 2 electron volts, or even from -1 to 1, and use thinner parameter for visualization, it may resolve this question. Last chance for more questions. If there are no more questions, let's thank Fatima once again. Very great. And we have one more presentation by Levi. He will announce the title himself.
So can I do it on my?
Yes, you can.
Yeah, I can just speak.
Not yet. Be ready to have it on memory stick.
I have it on Google Drive. I can just sign it. It says it's connected. Can I send you out?
Yes.
Yes. Go back.
So what do you do?
Just as the reading is.
What's your
Just try to change this file of the file. Can shove something while that can happen. It'll read it number by number and skip all the spaces. Just automatically.
So is this while loop is depends on how you open file?
It has to be green file.
It's still searching file.
Do you have any other,
I just wrote the word.
maybe there are any other format to read, another way to read the file. But this one work only maybe this one, this I think.
But we don't-
No, I
IN
mean,
is
we
just-
can open the file, flat and line or something like that. I'm just trying to make clear about this, using this.
So this file type open is the same as, so the N is the same as R.
Yeah.
Read, right?
Okay.
If you just do read, you can't write, you can't append. You
Mhm.
just-
That's fine.
That's all I'm doing.
Okay, good enough.
Okay, so today I'm going to do kind of a broader lit review. I am going to look at thiolate passivation of nanoparticles. The reason why I say nanoparticles is some of the journals that we have, or the papers, are on core shell, so cadmium solenoid, zinc sulfide structures. So that's why I said nanoparticles, even though we're interested in quantum dots typically. So the motivation for this, as I'm sure everyone in here knows pretty well, quantum dots are fairly photostable, highly emissive. One person that says tunable emission. You can manipulate the bands by ligands, and you can do band engineering. And in this, the research that this is related to, we're gonna be kind of working with someone, this lady, who has developed a whole bunch of quantum dots with a lot of different band structures. And this is very important to reduce the cons. So if we look at the cons for these quantum dots, if you have core shell structures, you can have lattice mismatch. Jabed has seen that in his, what's the J word? Janos structures. So it is very important that you try and get these structures to have ideal lattice parameters. Otherwise, instead of having nice bands like this, you can start and get trap states. I can send you that paper, Andre.
What now?
The paper with Janos.
Oh, we just discussed how to pronounce it.
Oh, okay. I have no idea how to pronounce it correctly. So core shell mismatch. Another problem is blinking. So when the quantum dot is emissive for a time and it drops off and it's no longer emissive, this can be mediated by these core shell structures, which is another reason why there's so much research on these. There's a whole bunch of complex surface chemistry and a lot of techniques for organic things don't work because like NMR does not work on the surface of the quantum dot. So it's relatively difficult for experimentalists to have a finite, to know definitely what's going on.
Janus quantum dot.
And then, as I kind of alluded to, the passivation of the quantum dots is kind of complex. So it's a very dynamic process where you have ligands come on and off, and the ligand might make the surface have trap states. So this is very, very complex, and it's also a very hot topic, making them water-soluble, surface trap states, and toxicity. Today, I'm mainly going to focus on water solubility and yes.
But wait, why does NMR not work, or what was that all about?
So NMR, do you understand how NMR works? Okay, so you have your nucleus spin that flip, and if you're in environments that allow that to flip back rapidly, the signal won't be processed by the machine, the NMR machine, and quantum dots facilitate the spin flip back, the nucleus to go back to normal, so you don't get the frequencies in the
Metal
NMR.
couples with the ligand nuclei?
Somewhat, yeah. So then it rapidly decays, and then it's either totally gone or very, very broad. So if you have two peaks that are right next to each other, and you're like, this one tells us that it's ligand A, and this one's ligand B, you can have two broad peaks, and then you're like, what peak is it?
Is identifying things.
Yeah, so like, if you, for our case, we have a thiol here, and you could do a proton NMR and figure out where this peak is, and most likely if you go to a quantum dot, that peak would disappear, because it's so close to the quantum dot that the signal decays so rapidly that you don't get any signal.
I don't know anything about MNR really, but I know for like some perovskite papers they've done like they can measure like diffusion.
Yeah, you can use NMR to learn stuff, but it's not as straightforward as throw a molecule in the tube, take this NMR sample and be like, oh, these peaks go here, these peaks go here, and then you can solve your structure. It's more complicated. Today I'm going to focus on water solubility and surface trap states. So first let's look at the easy one, water solubility. And this one can be kind of relatively straightforward solved. You can synthesize your quantum dots straight in water, which this is not the typical synthesis. You have a reducing agent that attacks your cacagenide, then you can make your cadmium cacagenide, and you can get very beautiful samples that already have the ligands on the surface that make them water soluble. So this ligand here, which is MPA, is covering the surface of the quantum dot right away because that is in the solution with water. And another thing that I'll talk about later is why these have the two functional groups at the end. The next way of doing it is if you do ligand exchange. So ligand exchange is exactly what it sounds like. You exchange the ligands. So one example from this paper, they have an amine on the surface, and in the solution around it, because it's a colloidal solution, they have the thiol-containing compound, and over time, the thiol will come in and kick out the amine. And then since the COO group or the carboxylic group is on the end, it will be water soluble. And additionally to just making it water soluble, depending on the R group on the thiol, you can make it do specific things. There have been papers where, and I don't have it cited, where you have two thiol groups and then you can make like a superlattice, and then all your quantum dots are spaced evenly and it's very well ordered. But that is kind of how to solve water solubility in the quantum dot. The next topic, which is the most important and relevant for my research, is surface trap states. Were there any questions on water solubility? I just want to nip it in the bud before moving on. No, okay. So, if you've been around the Kalina group long, you've seen this image many times. And this is the curse and blessing of quantum dots. Ideally, we want to have the quantum dot completely passivated so that there are no trap states on the surface because of dangling bonds. And a dangling bond is any atom that is undercoordinated. So a lot of times you have cadmiums that have 2 or 3 coordination, and they have a place where another species can bind, and that is where the ligands come in. Typically we don't have ligands that will bind to the anion. They typically go to the cation. So if they're ideally passivated, the band gap is open and the electronic structures are ideal. However, in the real world, you typically don't have ideal passivation. So like here's ideal passivation, here's not ideal, and you can see that there's disorder on the surface, and that leads to trap states. And in this research, we will be looking at a thiol ligand to try and see if we can either remove those trap states or enhance those trap states. We want to remove them, but yes. So yes.
So I don't understand how this can happen. So in solution of water, right? Why doesn't a water molecule come in passively if there's a lack of
So I haven't seen this, but I would assume that water would not act nicely to the surface, so it could oxidize the surface, and then you could make trap states. So typically, like these are all in organic solvents, so there's no water present. If you're in the organics, aqueous solutions, then there is, so we have the binding, and then we have the spot that makes it water soluble, and then in between it's all organic. So since it kind of makes like a shell of water soluble, and then in organic, the water probably doesn't pass as rapidly as these, so then they bind the thiol compounds and water doesn't penetrate into the surface. Does that make sense?
Yeah.
I'm just wondering, have you just said that water oxidizes on the surface of the
I
quantum
said it could oxidize.
That means
I don't know
water
when
can
it
split out?
happens. Huh?
Is it possible then oxidize, then water can reduce and all split it out?
Yes, this could happen. But if you oxidize your surface and you're trying to use it as a catalyst to split water, if you oxidize your surface and you don't reduce your surface, then your catalytic cycle is dead. So,
No, you mean in ground state or after excited state or
I
somewhere?
didn't say photooxidation.
Oh, yeah.
So experimentally, they use two similar ligands. One has the alcohol and one has a carboxylic acid for theoretical.
Before you go there, just answering your question, so technically it's just again an organic chemistry, so water is really water to coordinate with metals, right? The coordination is really having much weaker abilities comparing to this type of ligands,
I guess
right?
my question was more so what's causing the trap states? If there's an abundance of stuff that could attach after some time, why wouldn't it equilibrate to be well passivated? That's more of what I was questioning.
Without controlling it, just by itself?
Like he's saying steady state. As time goes on, if everything's if you have a solution that can passivate the surface ideally, why does it not do it? And I would say that you always have impurities. So if we go back to this one, this loses its oxide, right? So this is top, not topo, right? So it is super hard to control exactly what's in your solution. And even if you control what's in it, you could have side reactions, which then can produce compounds that are not ideal. For these ones, you can make a disulfide bridge, right? And then that disulfide bridge could either pop off, and then for some time you have unideal passivation that you have to let something else migrate in.
It's probably in dynamical equilibrium.
Yeah.
It's not really reaching to the steady state at all. So it means your ligands probably stays there, like one or two be substituted by something else. One or two might be completely lost, right? Or after some time they return back to this position. So you better control these processes than just leave it as it is.
And
again, empirical, not like you. It takes a lot of efforts to understand what's exactly going on the surface, and that's why no one really probably can clearly say, oh, it's because this and that. But it's very clear that if you just leave it by itself, you're losing the emission. That's without any explanation, the mechanism why it's losing its emission due to the trap state formation, right? No any other easier or better explanation rather than that.
And a side note, if you grow these chains longer, you have very flimsy alkane groups, which then can prevent ligands to be in the neighboring cadmiums because it takes up more volume. So then you might have cadmiums that are not even passivated because of the ligands themselves. So these are the ligands. Theoretically, what we typically do is remove the water-soluble portion because we're not simulating water solubility. And in experiment, they, as I said before, have two main types of quantum dots, core shell and just a single material. So for the core shell in this presentation, I'll be looking at cadmium. I should have denoted these different. So cadmium sulfide, zinc, cadmium solanide, zinc sulfide. And then for the non-core shell, I believe all of them are cadmium sulfide, solanide. And as I said before, these are nice because then you can do band manipulation. But even if you have these type of structures, if you make a very deep trap state, you could produce a trap state within your homo-lumo gap of your emitting core. So if you notice here, most except this one, they're all the core that emit light because that's the smallest energy. So if you have a really deep trap state on your core, you can make a trap state in here and it would still be non-emissive. So the first paper I looked at, they did looking at their experimental. They probably were looking at stoichiometric cadmium solenoid quantum dots, and stoichiometric means that the surface is 1-to-1 ratio. So it's not enriched with cadmium or selenium. It's probably a 1-to-1 ratio. And in this paper, they said that this ligand back over there makes a whole trap state, which is kind of weird because in their main text, they have this figure, and the figure shows an electronic trap state. So it's kind of weird to me. And then they say selenium vacancy, which also means that it should be a whole trap state because the DOS is the whole states or the conduction bands are mainly selenium, where the conduction is, conduction band should be cadmium, valence band should be selenium. So when they said this picture kind of, I didn't like so much, but this shows what they've seen and how they did this experimentally was they did it two ways. They took different concentrations of this MPA
And this is exactly the structure of this molecule?
yes,
I mean, no long tail or
No.
anything, just exactly as it is.
yes. And that's why I put it there, because if anyone asks, I'd be like, sorry that.
Can you pronounce it chemically, like mercapto?
I don't, nah. So it's beta mercaptoethanol,
Okay.
I think.
Now this is BME, and you have MPA. It's different name.
Oh, sorry, 3-mercaptopropioneric acid. So what they did two studies. They did concentration based and size dependent based. So in this one, the concentration of,
This is emission, right?
yes.
Emission spectrum.
So in this one, the concentration of the thiol is constant. Here it changes, and we can see that there's initially there's a well-defined band edge emission, and then there's kind of a trap state here. And as you increase the MPA, it goes up pretty dramatically, and the band edge falls off rapidly. And then when they did the size dependency, they also saw that the small quantum dots have more trap emission than the larger quantum dots. And both of these tell me that,
But it's emissive, right?
yes, it's emissive,
Okay.
but it's still making trap states that are emissive. This tells me that from these two figures, that concentration is very important. So if you have very weak, very small concentration, you should retain your emissive properties, where if you go to higher and higher concentration, you get less emissive band gap. Yes. And that's...
And present back, but with the size of quantum dots, is it normalized? Because your
Yeah, so-
main peak is not changing.
Yeah, so I think they set this as this in its normalized intensity. So they set
With the
the
larger peak.
yeah, the largest peak. And then another study, they used the alcohol form instead of the acetic acid one. And here if they didn't use the word phrase double-edged sword, I did, and the reason for that is here's the black line which has no thiol compound in it, and as we slightly increase it, the quantum yield goes up by like 60%, and then after some time, some of it drops. One stays constant, the smallest concentration, but if we go to crazy high, it completely quenches the quantum yield. And in this paper, they not only looked at the concentration, they also looked at the effect of pH. So this guy here,
So it's the same paper.
it's the same paper.
And which year again?
So this is
2005.
05. Yes.
And this is in a co-authorship with
So
Sergey
Sergey Ivanov, Victor Klimov, and then Jennifer.
Okay.
So then they looked at the effect of pH. So they set their standard with no thiol, and then they did it in neutral, acidic, and basic. And they saw that basic over about a few hours is trending to kill it, and then either neutral or acidic slightly goes up, and it has a higher magnitude for the acid form. And in their paper they said we can't really draw a whole bunch of conclusions from this because the trends or the results aren't dramatically different as it is for the basic. What I think happens is
And again, I missed. What is the green then?
the green is neutral.
Neutral in the sense pH. They just control it through the pH.
Yes, yeah. And I think that is around 9.8, 9.6, because that's the pH, pKa of this compound. So it's all depends on this guy. So I don't know who knows what pKa is. Okay, so pKa is if pH and pKa are the same, then the ratio of protonated versus non-protonated species are identical. If you go below the pKa, then you get more protonated. If you go above the pKa, yeah. So if you go below, you get protonated. If you go above, you get deprotonated. So if we take our knowledge of pKa and they're experimental, we can say that on the surface of the quantum dot, there is more protonated thiol than non-protonated because of the fact that if we're at the neutral here and we decrease the pH, we get more acidic, the more proton. So this has more of this compound, so the thiol.
Okay, I would put it
This
this
has
way.
less.
Your line blue corresponds to the red line on the middle graph, and the blue line corresponds to the behavior of the red line on your
Yes.
other one.
Yeah. So from here we see that thiol, not thiolate, so thiolate's the deprotonated, is important for having highly emissive quantum dots. And then the last study that I've looked at here, they looked at the long life, stability. So in the paper they say pH 8.5 in the figure, but in the text they also say 9.6. So it's kind of confusing if this is actually 8.5 or 9.6. But we see that if we're around the pH of the pKa, it is highly stable up to 3 weeks. If we start to go lower in pH, then it starts to die. And if we go really low, then it rapidly decays. And that could be a host of things, which I don't know. But it looks like if we have a pH around the pKa is stable, which also indicates from the last, so this paper said we want all thiol. This one's kind of saying,
So it's a different one.
yeah, this is a different paper. So,
Different doses, right?
yes,
Of the same author.
different authors. This paper is kind of saying that you might want to have a mixture of thiol and thiolate for long-term stability, because then it can be in like dynamic equilibrium, because they've found that
But this is photo stability, right?
this is,
What kind of stability is addressed?
I believe, so if I remember correctly,
It's not chemical stability,
yeah, it's,
photo stability.
yeah. So if you want to emit light after 3 weeks, it will still emit light. It might not be I don't think they did photo bleaching, so I don't think they irradiated it for 3 weeks. But I think they took the sample back out.
After
took-
some time,
yeah.
after some time, after some
Yeah.
time, okay.
So this paper said from DFT that thiolate binds to zinc sulfide wurtzite on the 001 surface. They did a slab of material instead of like a sphere, and then, oh, I missed an S.
Doesn't.
Thiol does not bind. So here they say thiol does not bind, where before it looked like thiol did bind and it had the best properties. So from this paper and the previous paper, it seems like we need to have a dynamic equilibrium between thiol and thiolate. Yeah, and the other thing that doesn't make sense is if the pH, so we see that pH around the pKa is stable over time. If that's the case, then these conclusions don't totally make sense, because you would assume that something's on the surface, and if the surface has the pKa, pH of the pKa, then you should have thiol, not only thiolate. So then the conclusions, high concentration of thiol on the surface introduces trap states. Then the trap states could be reduced by forming the thiolate ion, and then this can reduce the trap states. The quantum yield of photoluminescence is sensitive to the pH. This is due to the equilibrium between thiol and thiolate. If you have very, very low pH, you can do some extra chemistry that we don't know about, or if you have very basic, you can pull off your thiol. And then the last paper was that for the core shell structure, the PL from 7 to 9.5 pH is stable for long duration. So there were a few open research questions that I kind of had from this, and these are also the ones that are kind of going to somewhat be answered with the papers that we're going to be looking at. So what is the ideal ratio between thiol and thiolate? This is important because if we know what the experimentalists need to achieve, then they can design experiments to see if our conclusions are correct. So if we say, oh, we need 1-to-1 ratio, then they could make quantum dots that are enriched with one ion or another, and then one will preferentially bind to different sites on the surface, and then we might be able to reach this ratio between the thiol and thiolate. Does temperature influence the equilibrium between the thiol and thiolate? Does dielectric constant? The reason why dielectric constant is important is from physics 1, we know that, physics 2 maybe, that the
Physics 3.
No, this is basic. So Coulombic interaction or dipole-dipole interaction or anything between partially charged species is dependent on the dielectric constant, inversely proportional.
Yeah.
So if we have water, which has a dielectric constant of like 80-ish, versus organic compounds that have dielectric constant is around 3 or 5, this will change dramatically. So this needs to be investigated. Where are these trap states localized? Are they on the ligands, or are they on the surface? This could help tell us what is going wrong and trying to fix it. And then, as I have shown, most of this research has been on the core shell, cadmium sulfide cadmium selenide zinc sulfide. So do the trends hold for cadmium sulfide? The reason why this is important is the experimental collaborators, they are looking at cadmium selenide, cadmium sulfide quantum dots instead of the zinc. So with that, I would like to take questions.
Okay, well, thank you.
Were all those papers with the solvent water?
No. So
My question then is, how do you define pH in an organic solvent?
So how do you define, I would say you define it as this you do in an organic water, right? So pH, it's not really the H ion that you're looking for, it's the hydronium ion, right?
pH is based off like auto-ionization, right, of water. So how does that, like if you're dealing with an organic solvent, how do you get it?
This one is kind of pKa. What is the pKa?
So
is from?
let me see if, so here, it is much more difficult to do it in organic solvents because of the things that you are alluding to. The thing that you can look for is the compound that takes the proton, right? So water pulls the proton from another water, you make hydroxide and hydronium, right? So it can acid base, I forget the term for it. So the ammonia can pull out the hydrogen from the thiol. So like this is the replacement for your water.
So that's like your standard.
Yeah.
So you base it off that, right?
Yeah. And I think all of the ones that they do the pH in, they either add an organic acid, and then I would assume that they look at the pKa, or they do it in water.
Oh, they just put their samples in water? Or
So this one was done in water, right? So this one's easy to do the pH. The other ones I didn't really read into.
You know, because I know one problem is like a lot of, or at least perovskites anyway, they're not water soluble, or the materials themselves are water soluble, so it's like you can't put them into water.
Yeah.
And same thing with probably some other.
Yeah, these are slightly soluble salts. So they would only decay very, very slow. I think the KSP for cadmium sulfide is like 10 to the negative 21st. So not
around for a while.
Yeah.
So if you had all your surface trap states filled, would you expect 100% quantum yield?
Yes. So I didn't show them here, but in more recent papers with the core shell structures, they can get like 100%, and they can even go above 100% because of carrier multiplication.
But if it was just like, I don't know, what it looked like first order, not like.
Yeah, so
second.
I think they can get near unity. And Svetlana was saying, I think last week, that cadmium telluride nanorods are defined as 100% quantum yield. So that's like your internal standard. Is that correct? cadmium telluride quantum rods are standard for 100%. I thought that's what you said last week.
Well, yeah, it's used as a standard, the most emitting species.
No more questions?
Last chance. You did? Last chance to ask Levi a question. If no, let's thank you once again. So, this was the journal reading club, paper reading club. On Tuesday we have paper writing club. So, if you are participating in this Tuesday activity, please consider to complete next section, which is methodology, right? And the in a week from now there will be a week another journal club and one practice presentation by Daniel for his second year. Okay, meeting is dismissed. Thank you for participating, attending, and have a nice weekend.